How old is the Earth? That question had been occupying the minds of scientists for many hundreds of years. It had taken many discoveries to get us close to a conclusion to that question as we think we are today. The first step on the way to an answer was taken by the Danish scientist Niels Steensen when he formulated the theory of superposition. When a mountain is eroded, the materials that form the mountain will be transported away by wind, water, or ice. Where the ice melts, the wind dies, or the current ceases, the materials deposit. This is what gives rise to the principle of superposition. Niels Steensen said that younger deposits rest on older, which means that the closer the deposits are to the surface, the younger they are. With the principle of superposition, we can determine this layer to be older than this layer. Fossils are often found in deposits. Fossils can play a crucial part in the relative dating. If fossils of a certain species are found in two different deposits, the age of the two layers can be determined to be near identical. With the relative dating, it is possible to determine one layer's age compared to another layer. It is useful in many cases, but without a method to determine the exact age of one or more layers, we'll never be able to determine the age of the Earth. Determining the age of a rock is what is known as absolute dating. The absolute dating method relies on radioactive isotopes. Radioactive isotopes are very common and many thousand different kinds are known. Each isotope have a unique half-life. Half-life determine how long it will take for half the atoms to decay into another isotope. Radioactive half-lives can vary from a fraction of a second to billions of years. The common zircon crystal can sometimes grow to large diamond-like crystals. Within zircon's crystalline structure, a radioactive isotope is found. Zircon are found in small amounts in many different rocks, like in this granite, and when the radioactive activity is highlighted, the zircon crystals become visible. Before the zircon crystal is formed, the red uranium atoms move around among many other atoms. Uranium-238 decays into the blue lead atoms with a half-life of 4.4 billion years. When the zircon crystal is formed, the atom settles into the crystalline structure. The structure doesn't allow the lead atoms to be apart. Therefore, in a newly formed zircon crystal, there's only uranium atoms and no lead atoms. After the formation of the crystal, the uranium will continue to decay and thus capture the lead atoms in the crystalline structure. As time passes, the amount of lead atoms rises while the amount of uranium atoms decreases. So, the age of the rock can be determined by investigating the uranium to lead ratio. The more lead atoms per uranium atom, the older the rock. If a rock is formed when liquid lava or magma is cooled and solidified, the absolute dating method can be used by investigating the uranium and lead content of the zircon crystals. Volcanic ash is liquid when it leaves the volcano in an eruption and solidifies in the atmosphere. If a deposit is found which contains volcanic ash, the absolute dating method can be used to determine the age of the layer. The age of the surrounding layers can be determined by the principle of superposition. So the accuracy of the age determination will increase the more deposits and rocks that are dated. Since the uranium to lead decay happens over such a long time scale, it can be used to find the oldest rocks that have been formed on Earth. In Australia, zircon crystals have been found with an age determined to be 4.5 billion years. No rocks have been found that are older than those, and thus we can determine the age of the Earth to be slightly older than the oldest zircon crystals. Based on that assumption, we can determine the age of the Earth to be 4.6 billion years. Thanks for watching. Please subscribe to the Goodrick Science channel and please leave a comment below. You can follow Goodrick Science on Facebook, there's a link in the video description.